In this video, I share some ideas from Chapter 12 of the Brown-LeMay-Burston textbook, Solids in Modern Materials is the focus of the chapter. I'm going to look at the structure of crystalline and amorphous solids. In the BLB textbook here, this is the best general chemistry textbook I know of for looking at the structure and description of solids and modern materials. The co-author and my friend and colleague, Dr. Pat Woodward, this is his area of expertise, and this is the best textbook I know for these ideas. If we look at the topics within here, classification of solids, that's found in all general chemistry textbooks when it comes to solids. The BLB textbook does a great job describing the structure. The categories, metals, ionic solids, molecular solids, and covalent network solids, those are common for all general chemistry textbooks. And the idea of bonding, metallic bonding, that's also present in all, although oftentimes it's only discussed in terms of the sea of electron model. This textbook goes beyond that and describes a molecular orbital description. Learning objectives within the textbook I list here, there's quite a few. Key ones that we include in our class would be listed there for 12.1 and 12.2, describing the types of bondings, the bonding interactions, and compare and contrast crystalline and amorphous solids. The chapter goes on. Very common learning objectives would be to describe electron C model for metallic bonding, looking more closely at ionic solids, and also the structure of covalent network ones. So some instructional considerations to share. I want to consider, well, how does a topic in Chapter 12 appear in BLB, and how does it appear in other general chemistry textbooks? When I say that the BLB textbook has ideas that the other ones don't, let me point those out to you. Let's consider if there's more to learn about the idea, and usually the degree of comprehensiveness found in BLB, it's a very solid textbook on these ideas, no pun intended. So I think that's oftentimes going to be sufficient for us. I want to share a little bit how I include the idea in my class, and I'm always looking for possibilities to integrate solids with other ideas. Chapter 12 is currently placed at the end of the first semester, and so we've got a lot of different ideas that we can bring together when it comes to connecting them to solids, especially with the cumulative final coming up. So to begin here, 12.1, I'm showing some text here from the Brown-LeMay-Burston textbook. So right here we're having a description of solids and different properties listed. When we're thinking about solids, the structure-property relationships are very important. What is the structure of the solid, and then what are the resulting properties that leads to? And it's pointed out many times that's dependent on the type of bonds that are present. So we at this point would look quite a bit at ionic solids, molecular solids when we have the idea of intermolecular forces present. Two new ones within this chapter are looking more closely at metallic solids and also covalent network ones. So within here we have a description of the 4 different categories, and then also quite briefly what these are like at the particle level. This now is sharing aspects of what the bonding is like. The chapter goes on and gives more detail, but it's given a description for each, whether it's a metallic solid, an ionic, covalent network, or molecular, and how that leads to different properties. Goes on a little bit to say that those particular 4 categories, that's not the whole story. There's also other types of materials, polymers and nanomaterials would be examples. What I like within this one is so much of the textbook leading up to this point, we're describing what's already found in nature. Different liquids, different gases. Those are examples that we have again and again. But in this chapter, we're beginning to think about, well, how can we manipulate and make new compounds? How can we begin to make new materials that will have different properties? So instead of saying chemistry is just analyzing what's already found in nature, I like the way that as we begin to think about materials, we're thinking about how a chemist in material science makes materials that will have technological applications. The types of questions that are on this very first part, I show 3 examples here from the end of the chapter, where given a formula, we're asked to classify it. Is it molecular, metallic, ionic, or covalent network? Descriptions here of the different properties, and as we're beginning to think about the structure of property relationships. And these bottom ones, a little bit higher on Bloom, where we're given a description and we need to classify this. Is this an ionic solid? Is this a metallic one? Typically on our exam, I think would be 12.17, 12.18. Those are quite representative. Now, in 12.2, it begins by contrasting crystalline and amorphous solids. If we're looking at this one, it opens by pointing out that solids contain a very large number of atoms. As I think about how I could integrate a piece of information like this, notice I've got the volume, I've got the number of carbon atoms. So this would be one where I would revisit aspects of dimensional analysis that we looked at way back at the beginning of the semester. Begin to think about, well, what would be the density given that information? That paragraph goes on to describe, you've got so many atoms there, how could we begin to describe such a large collection of these? To me, this is the most important conceptual idea when it comes to solids. We could live in a world where every single solid had its own arrangement for how the atoms were put together, how they were structured, their geometrical arrangement, but that's not the case. The structures of many solids is said to have a pattern that repeats over and over again in 3 dimensions, and we're going to find that these patterns, we can make sense of them and see common features across them. So the most important conceptual idea when it comes to solids is this idea of the smallest pattern that repeats again and again. And even though these give rise to different solids, there's some common features that we can look at for how that happens. So to me, that's the key thing when I'm trying to think conceptually what makes something a crystalline solid. When I say crystalline solid, this idea of having the smallest unit that repeats again and again, that's not true for every solid. It describes here some characteristics of a crystalline solid. It's one right here where we see this clear face, this clear geometric pattern, that's a crystalline solid. This one here on the right-hand side, that's an amorphous one. When we're looking at crystalline versus amorphous, the amorphous solids, they lack the order that we're going to find within a crystalline solid. At the atomic level, they're very similar to the structure you'd find of a liquid. So this is going to be useful for me because this is going to give me some insight into how I think about liquids as well. There's listed different examples. Rubber, glass, volcanic glass are all examples. The one that I'm most familiar with is a type of glass called a tektite. This is something that was part of my my graduate work. I became an expert on tektite. So let me share a little bit of information about that. Here's some examples of different tektites. How large are they? You could hold one in your hand typically, not any larger than that. Tektites are glasses formed following a massive impact. The description here is, imagine you have the different initial minerals are present. There's a massive impact that melts and vaporizes that solid. If it's rapidly cooled down, which is called quenching it, you can lock in that melted structure and turn it into a glass. This idea of taking something, melting it, and rapidly cooling it, that's how you form glasses. On Earth, there are these different, what are called strewn fields, where tektites are found. They're different from different eras. Okay, they weren't all formed at the same time. There's one in the southern U.S., one on the Ivory Coast, Moldavia, and a large one in Southeast Asia. So when I began looking at this, it wasn't clear. Were we looking at something that was due to a terrestrial impact or a lunar one? Had something smashed into the moon, taken that material, formed that into a glass, and had that then enter Earth's atmosphere and cover a particular area? Studies like this one, they appear in journals like Meteoritics. So there's a whole field of this of looking at different impacts, and tektites would be an example. Quite popular on that would also be the impact at the Chicxulub crater, which popularly is described as leading to the demise of the dinosaurs. Now, when I talk about glasses here, there's certainly technological applications for this. Here's a video that I just grabbed off of YouTube. That's a promotional video from the premier glass maker, I believe in the world, Corning. So this was back in 2012. So Corning is involved with making high-tech glasses. So what they're trying to do is show different kinds of applications where these could be found either in one's home, in industry. So they're trying to give you this futuristic view of how might different glass surfaces be used. I also find it interesting what aspects of this have come to pass and which ones have been replaced in different ways. Right now, Corning, a large part of their business is making the surfaces for iPhones. Now, beyond technological interest, there's a lot of geological interest in glasses because the structure of a glass is like that of a liquid. So we know that if you move closer and closer from the Earth's surface to the Earth's core, we get different molten minerals. So those particular liquids, if we want to understand what they're like, by understanding what the analogous glass is like, we can get insights to what would it be like geologically as we move to the Earth's core. That to me is also gives me a reason for understanding glasses pedagogically. How do we think about a liquid? So I'm grabbing this PhET sim here. We see water molecules jostling around. We know that they're attracted to each other. Intermolecular forces are acting between them. I'm seeing a dynamic motion. I'm sort of seeing a pattern here, but it's not altogether clear. If I were to look at one particular molecule, it seems like again and again, the most immediate neighbors around that seem pretty similar. That's called the first coordination sphere. The different particles that are most immediately adjacent to it, describing the local environment. I see within here that the coordination number, the number of neighbors that it has, it's fairly constant in the liquid. Might be 6, might be 7, it's changing a little bit, but it doesn't dramatically change. It's reasonably ordered for what I find around that particular molecule. But if I look further away, I don't see a pattern that continues. It lacks what would be called long-range order. There's not a symmetrical pattern in a liquid or an amorphous solid. So this was being shown for a liquid, but if you were to lock this in, this would be what you'd find in a glass too. Here's another PhET sim showing different states of matter. So it starts with a solid, considers what happens as you add heat, and you begin to disrupt the pattern. You're disrupting the long-range order, but most locally, that first coordination sphere, it's remaining pretty similar in terms of the neighbors that are found there. And if you were to lock this in and quench it, stop the picture, that would be a description of a glass. So when students ask me, okay, what does an ionic solid look like when you melt it? I always get that question. What would I imagine? I would imagine you begin with the ordered ionic solid, that has both short range and long range order. And now just let's increase the vibrations. Let's increase the motion such that I'm largely retaining the most immediate neighbors, but it no longer has this extended pattern that goes in 3 dimensions. Network covalent solids, SiO2 would be an example. Here we see a crystalline one, and then here we see the amorphous. So we still have this local environment, but we don't have the long-range order. A glass, as you might imagine, it has a higher entropy than the solid. Now, here I've talked about a couple examples, bringing it back to something your students would be familiar with, different candies. So this is now involving molecular one. This is involving sugar. Lollipop, taffy, caramel, these are all examples of amorphous solids. So that was a look at the amorphous one. I contrasted that a little bit with crystalline. Now let's look more closely. And when I talk about this ordering, this long-range order, how is that coming together? So we have right here a description of unit cells and crystal lattices. So first of all, we've got this repeating pattern again and again within the solid. What that needs to account for, it needs to be able to describe the resulting structure, and we need to consider factors like, does it get the correct location of the atoms being found such that we can have this pattern repeat again and again to give us the overall 3-dimensional structure. Key thing that I find right here in BLB that I don't find in any other general chemistry textbook is this idea. So we have a crystal lattice. This crystal lattice, which is going to be describing this resulting 3D shape, BLB will make the point here that this is an abstract scaffolding for the crystal structure. The crystal structure is not the same as the scaffolding. It is a way that we can build together the crystalline solid, but the crystal lattice that we have here, this particular arrangement, is not the crystalline solid itself. Let me show you what I mean by that. So let's say you had this old tray and you're going to make ice cubes. So you can imagine that is providing a scaffolding. It's showing where the water could go. So at least in theory, you could fill it up, you could freeze it, and then you could pull away that metal scaffolding there and still keep the symmetric pattern. Now, that would be your scaffolding. So let's say in each of the holes right there, along with the water, you put a cherry. When you removed it all, you would then have a pattern of cherries that would be going throughout. The scaffolding gave you the pattern for where the cherries would then be found. Now, it wouldn't have to be just one cherry. Let's say in each of them, you put a cherry on the left, a blueberry on the right. Cherry on the left, blueberry on the right. In each of those, you are now putting 2 items. And then after you remove the metal framework for it, you'd have the resulting pattern. So that's what it says. That's what it means. It says when we can imagine forming the entire crystal structure by first building the scaffolding and then filling in each of those unit cells with the same atom or a group of atoms. The scaffolding was this framework. And within those, I was putting in this example a cherry and a blueberry. Let's look to a chemistry example or two, and I'll show you what I mean. So the BLB book begins by saying, let's think about it first in 2 dimensions before we go to 3. So in 2 dimensions, what we're doing is we're trying to get a pattern that we can repeat again and again to fill up all the space. No gaps are allowed. So in our simplest description here, we could see that this particular shape right here, if I repeat it again and again, it's going to fill up all of the space. This idea of taking a simple pattern and repeating it again and again to fill up all the space, turns out there's only a very small number of shapes that can do that in 2 dimensions. A square certainly could. A rectangle certainly could. We see that we have 5 different examples of shapes that again and again can fill up all of the space. It points out that other polygons, even relatively simple ones, cannot do this without leaving gaps. Great example here would be if you had something that's a pentagon. You can try to fill it up the best that you can, but you'll still have gaps in between. An analogy I often bring up would be if you're doing tiles in your kitchen. You need to have a particular shape that will fill up all of the space. You can't make it five-sided. If you were to take this now and take it into 3 dimensions, instead of having a square, you could say, okay, let's make it now 3 dimensions and turn it into a cube. Let's take our rectangle and make it an orthorhombic shape. So all that we've done to get to 3 dimensions, we've added, obviously, 1 more dimension to our shape. And we see that now we have a small number of those that can fit together again and again to fill up all the space. Now, sometimes we have lattices that also have additional lattice points present. This is something that we include in our class. So for a cubic one, we could put lattice points at all of the corners. Bodied centered would put it at all of the corners and 1 in the center as well. Face centered would be putting it at all of the corners and 1 along each of the faces. Sort of like what a dice would look like. Now, remember that these the lattices that we just mentioned there, these are like our scaffolding. We now need to fill these up. The lattice by itself is not giving us the crystal structure. This paragraph right here I think is quite telling. To generate a crystal structure, we need to associate an atom or a group of them with each of the lattice points. Now, in our simplest example, each of those lattice points would be where an atom is found. Points out that many metallic elements will have such structures. But this is only for solids in which you have the same atom again and again throughout the entire solid, like an elemental form. That won't occur for something that's a compound. Sodium chloride, for example. You might say, well, what if I put a sodium at one of the lattice points and a chloride at the next, and I fill up my pattern that way? That's breaking the rules. Each of the lattice points must be equivalent. So this idea right here of saying that the lattice itself does not define the crystal structure, we need to figure out what is associated with each of the lattice points. Again, that's something I find in BLB, but not in other general chemistry textbooks. So what are we going to associate with each of the lattice points? What we associate with each of those is, it can be a group of atoms, it's called the motif. This is what's associated with each of the lattice points. This is what's going to be combined with the lattice structure there to build up the overall compound that we have, the overall solid that we're looking at. I really like this example here for graphene. So what we see at the bottom right here, 4 points for a unit cell. That would be repeated again and again, and it would fill up all the space if we just look at that shape. In this example, the motif are these 2 atoms that are being placed within that unit cell. Doesn't necessarily have to put an atom at the lattice point. This is just giving me the pattern that repeats again and again. So notice as I add those, I can fill up all of the space that way. And then if I remove the structure, the outside scaffolding, that's the resulting arrangement that I'm left with. I'm thinking back to my example with the ice tray. The ice tray provided the initial walls that gave the scaffolding. I could have my cherry and my blueberry within that. Then after everything's in there, I can imagine those walls coming out and I have the resulting pattern that is found. As is pointed out here, a couple of things are taking place. We had no atoms being found right on the lattice point. We don't need that. The lattice points are just providing, again, a description of the scaffolding. And when we're thinking about the bonds, it's not the case of bonds only taking place within the motif. It's resulting in the overall structure. So in a way, the lattice points, they're not bossing around where the bonds are formed. They're just giving us a way to understand the pattern that's going to be produced. So here we're looking at ones where we're looking at metals. So within metals, an elemental metal like gold, for example, the motif can be just that particular metal atom. You could place it at all of the points in a primitive cubic lattice. That's what it's showing at the bottom. It's combining the motif with the crystal lattice to get the crystal structure. Or you could take the metal atom, have it be bodied centered, all of the different corners and one in the center, or the motif and making it face centered. These are examples of putting the atoms as a single, the motif as a single atom being placed at all of the different lattice points to give rise to the crystal structure. Now, the way that these are drawn, a particular atom, when we see it here at the corner, it extends beyond that single unit cell. It's being shared by all of the adjacent unit cells. This is an idea that we include in the class. So if we have one of these, like this red being shown at, could be at the corner for this unit cell right here, but it's being shared by a total of 8 different ones. That's what it's trying to show, the way it's sort of hanging over the edge here. So one thing that we do is we practice accounting for, is a particular atom within a unit cell? Is it partially within a unit cell? And if it's partially, how do we count its contribution? So if things are at the corners, those all count as a 1/8 contribution because a particular atom there is being shared with 8 different unit cells as neighbors. In a bodied centered, we have the 8 around the corners and then 1 that's in the center. If it's in the center, it's not being shared at all. Or what happens if it's on the face? If it's on the face, it's in 2 different unit cells. So here I show what happens if we have some ionic compounds. So in this case, the motif, it has to be more than just one atom because we have to end up with the compound. So for example, in cesium chloride, the motif are these 2 atoms right here. They're going to be now placed, in this case, at each of the different lattice points. And we find that within that, it will give us the pattern that reproduces again and again. Notice for cesium chloride, if I were to take this and say, what is the empirical formula? I see 1 cesium atom entirely within the unit cell. And I see a total of 8 chlorides, each with a 1/8 contribution. So cesium chloride empirical formula is 1:1. The reason that we don't see more than 1 cesium atom, the next one would be present in the adjacent unit cell. See if you can sort of visualize that in 3D. That idea of seeing how it extends in the next one, for the sodium chloride, I can probably see that the easiest. So I see that at this particular lattice point, there's a chloride in the sodium. At the next one, at the top right, a chloride. Where would the next sodium would be found? It would be right over there in the next unit cell. So in each of these, we have two atoms being found associated with each of the lattice points, and that's what's giving rise then to the resulting 3-dimensional unit cell. That idea of being able to analyze and describe how many atoms are within a unit cell, here's an end of chapter question. It's asking us to analyze these and consider the density. Notice within both of the ones for structure type B and C, how many atoms are within the unit cell? Well, within this one, I clearly have 2 within the unit cell. How about for structure B? There's 1 in the center, 1, 2, 3, 4, 5, 6, 7, 8 on the corners. So both of these, even though the pictures look different, both of these have a total of 2 atoms per unit cell. Oftentimes, typical question, give a representation like this and ask for the empirical formula. I see 1 titanium in the center, entirely within the unit cell. I see 6 oxygens, each along a face. I see 8 strontiums, each at a corner. That's what I would use to come up with the empirical formula. Here's another example. Here's one going back to the idea of being able to think about the lattice points. Can we draw the unit cell? We're looking for the simplest pattern. In part C, it says how many atoms of given type white or black are there per unit cell? I look at this one right here. I see one black entirely within there. 1, 2, 3, 4 of the white, each with a 1/4 contribution. So it looks like this would be a pattern that has one black and one white. If you thought about it that same way there, I think it leads to the same result. Either of those would be a two-dimensional lattice that could be repeated again and again to fill up all the space. How about in example 2? We're looking for the simplest pattern that we can have. Is this the simplest pattern, or is there another way that you could construct it? So within this particular video, briefly looked at the types of interactions when we're looking at different types of solids. When we're thinking about crystalline amorphous materials, crystalline ones, that's the one that has its repeating unit cell again and again. Amorphous solids have a local order that resembles that of a liquid, but they do not have a long-range order. They do not have a unit cell that repeats again and again. In this dash section here, this is looking more closely at how we combine a motif with the lattice to end up with the crystal structure. I'm putting it in dash because in some ways this is a higher end treatment than what you find in other textbooks, but this is what's actually going on. In this case, the BLB textbook gave us some deeper dive information.